Greetings, everyone. Let's cover a few sections from our chapter 5 in the book. Then I want to bring your attention to some of the slides that I have that would complement and hopefully add more value, supplemental value to the content that's here. We begin by what is regression modeling? Well, we have a couple of big terms in here. We all know about the x-axis, and we're all familiar with the y-axis, goes up and down. But in here, the x-axis, interestingly enough, is also known as predictors or features. For example, square foot of home and house prices. Suppose the larger the house is, the more the price it might be. And of course, there are some outliers. Certain homes in a downtown locale might only be two-bedroom, yet governing a really high price. Or you might find a five-bedroom house somewhere out by the Berkshires, if you would. And, well, it won't garner the same amount. So how do we come up with a fair price if somebody comes up and says my house is 4,300 square feet? What might be a fair price for my home, a fair price? Very well. Hence linear regression analysis. And this happens to be linear because, well, it's a straight line. Ordinary list squares. Now we're seeing a lot of formulas in here, y hat and so forth. I have another slide in mind for you that I would like to elaborate on this as we get to it. The measure of R2, it's an important measure. Notice how some of these blue dots are darker than the ones that are further out. It means the variance of the independent variable predicted by the dependent variable, the x-axis. The ones that garner a darker color happen to be a better fit than the ones that are out there. So this means a goodness of fit can produce dots that have a tighter model and a higher R square value. This is an interesting story in here, especially the one in this box in here. The key difference between descriptive, explanatory, and predictive modeling. You could also change this word modeling to statistics. And then what you would have, basically, in the world of data analysis, data analytics, data science, you have descriptive statistics. It describes how it is. A mean, mode, statistical significance. These are descriptive. Then you get to, well, explanatory is the same thing. And then you would get to predictive. All right. So now thank you for describing how it is. Now, how might it turn out? If I regression, let's look into the past and try not to do the same in the future. And then, of course, there's prescriptive statistics. Prescriptive, like prescription. So that means, okay, so now what do I do? I found out what is happening. I can predict how this might turn out. So, what do I do now? Do we remove outliers? Do we have to put in certain values to get better? Do I need a higher accuracy? Do I need more recall? The main focus is retrospective or prospective models use and report either interprets or predicts, dare I say, and also prescribes. What do I do next? And this is interesting. I want to spend a little time talk about. The data set is used and divided into training and validation sets. These are important. And then we have the k-fold number of folds that you may have in doing this. You could say, I want to spend some time talking about absolute mean error or the square root. You could say that this is the simplest machine learning algorithm. It is designed to predict. We see it common in statistics, but and it's very much also an algorithm for machine learning. Training data validation test set. Notice there's three of them. I want to chat about this in more depth as in one of my other slides coming up that perhaps would shed an easier light on this story. And then there's the notion of folding. n-fold or k-fold? How many times can I fold my training data set? Very well. And of course, this thing called dummy coding, it's not so much of a term that I come across in my 22 years at IBM as a data scientist, but I suppose it's assigning a numerical value at a place that it would make more sense. So it's in a sense, it reminds me of one hot encoding. Overfitting is a very interesting and a common occurring problem. Let me read this for you, and I'll ask you how much did it make sense. When the model has too many independent variables, multicollinearity is possible. The predictor variables are highly correlated. The size of the coefficients are incorrect, or the coefficient signs may be reversed. I'm trying to wish I could see your faces and and the one that says, okay, I got it. So let me explain this, the notion of overfitting that you're also familiar with. Uh, let's say here we are, the professor asks you to study chapters 1 through 5. Just as what we're doing here. And you have an exam, let's say, coming up next Thursday on chapters 1 through 5. Now, these are really nice and robust chapters. They have the questions at the end of each chapter. The answers are in the appendix. You try to answer the question on your own. You might get some, you might not. You'd look at the appendix, and then you would go, aha. That aha, my dears, is what we call learning. And so you're ready. You've gone through the exercise question answer pairs in the book, and now you're seated at the exam. It's the Thursday, the following week, and all of a sudden you notice that the professor is giving you the same questions that were in the back of chapter 3 and 2 and 4, and you're looking around at your friends sitting to the left, to the right, going, "Wasn't this question in there? Everyone's going to get an A." You're starting to wonder, actually, about the professor's acumen in teaching here. That's overfeeding, and we want to avoid that. Anything interesting in here? I want to chat about these. Feature selection. Feature selection is a big thing. The lab that we do using Auto AI features feature selection. They actually call it feature engineering. Um, Dr. Seffield once said to me something that is stuck in my mind. She said, people don't care how much you know until they know how much you care. So I'm reading in here and I'm wondering, as I'm going through these, how much caring has taken place in helping you understand and come up with that aha moment. Well, this goes on. The case study in here, I won't go over it because our case study is about the insurance company. Bear with me, my dears, as I bring you over to my set of slides. Let's do a slideshow from a current slide. All right, method of least squares. This is my error, E, error. And I want to minimize this error. None of these dots I don't want them to be too far, for example, from the line. And of course, one's happiness is another's misery. But this line in here needs to do justice to all my data points. All right, let's do a little Picasso in here. So, y to the, I know where y is. Here it is. Tack, 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 tack. Thank you very much. That's given. What about y hat? Let's bring on the Picasso. Y hat, my dears, this is how you calculate it. Y hat, and you will recognize this formula from the PowerPoints, is equals to mx plus b. That's right. B is the y-intercept. It could be negative amount depending on where this is. It could cross it over here. It could cross it over there. I need to know where my predictive line would cross the y-intercept. This is my bias in here. In this particular case, the x is 0 and comma, and wherever it hits the y, we call it b. This actually is in the industry, no matter what company you use for, this is the formula used. Y hat means predictable, equals to mx plus b. Now what about m? M is my slope. And I do know what x is. It's just tuck, tuck, tuck. There it is. And I know what x is. So m, slope, as you might remember, is equal to y2 minus y1 divided by x2 minus x1, right? That's how we calculate slope, right? If I want to calculate the slope, I have two dots in here. Here's my triangle, right? And I can go tuck, 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 x2, and over here, tuck, 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 x1, got it, x2 minus, and y2 minus y1, up over here would probably be somewhere here, y2, and if I take this, go all the way, it would probably be here, y1. Then, interestingly enough, the slope is also known as derivative. So, derivatives and integrals is the area under this line or curve, and the derivative is the slope. And that is the trick behind when they say artificial intelligence, that's where the intelligence comes. It is the machine that goes through this iteration and finds out what the best slope is. It's not the human that tells it. And notice we have squared them in here because, this would be a negative number. This would be a positive number if you subtract them. So let's make everything a plus number, and we sum them up. I want to know the difference from here to here, the difference from here to here, this one, all of them, this one, and square them. That is the method of least squares, which will give me exactly what I was working for. Now, where is this used? How is this used? In the next chapter, where we get more into machine learning, I'll take a step further and I will put this into a regression analysis that actually uses machine learning. For this chapter, I want to bring your attention to what the book was talking about earlier, called training data and holdout data and split data, training and holdout methods. This is a screenshot from the lab that we did with Victoria, and I had asked her to move this around. And when you do this lab, I recommend you to do that. So the machine says, oh, wait a minute. Holdout data is reserved for calculating performance metrics, or this blue line. This is the study. This is chapters 1 through 5, right? That's to be studied. This section over here is what we're going to be tested on. So right off the bat, from the very beginning, the specific CSV file that we have for this course, 975 rows. Let's say it's 1,000 rows. All right. So with that, we say, machine, I'm going to take 10% away from you. We moved this back until this ended up saying 90, and this one was 10. So just to keep it within kosher limits, sound limits. This is a lot like the professor taking away a whole bunch of those question answers from chapter 3 and 5 because he or she wants to use those for the exam, and you're left with 2 handfuls of questions to study an exam. That's not very helpful. So what do we mean by trifold? So those were 1,000 rows, right? Let's say that's first 300, 300, second 300, that's 900. This over here, I'll put it like that. It's the rest of the 100 rows, and we take that away from the machine. Minute 1, the machine never sees these, does not see these past 100. That's 100. So we got 300 rows here, and 300 rows here, and 300 rows here. Great. So the machine says, all right, I got this. I see the answers that you have provided, supervised learning in this instance, true, false, yes, no, 1, 0. It's but dichotomous, bimodal, logistical regression. It's an S curve, sigmoid operation, to be elaborated upon on next week. But for this purpose, we're saying, all right, machine, this is what you get to study. The machine says, fine, you want me to do a trifold, huh? So I'm going to break those into three segments. I will study all that's up here. Let me get my color going. I will study all that's up here, find the patterns, and then I will study all the stuff that's down here. The third one, find patterns. I will close my eye and see how well I can guess the middle. And then I'll do the opposite. I'll do the same thing. Let's pick a different color here. Let's say that. I will study this section, find the patterns. I will study this section, find patterns, close my eyes and see how well I did here. And of course, the third fold is a lovely color to work with. It's going to be this bottom two. So the machine is looking for patterns to see what bunch of columns are a telltale sign of why a certain column would garner a 1 or a minus or a 0 to its classification. There's a pattern that it does. That is the story of trifold building. And when we came up to this section later on, and as the book also mentions, the notions of feature engineering and the hyperparameter features really are those columns that we were looking at in our show. And feature engineering means, hey, multiply two of these columns, make a new column, put them over there, subtract them. If the number is minus, give it a 0. If the result of your subtraction is a plus number, give it a 1. Or some such, and 1 means this, 0 means that. So feature engineering, you know. Take the sine, cosine of 2 or 3 of these columns, because it might be more than one column that happens to be telltale sign of why one might do fraud on their automobile. This was also a very interesting model evaluation we came from. And this tells the tale of something known as the confusion matrix. And I want to keep that separate from this. And, as a data analyst, as a data engineer, I'm not talking AI engineer, machine building monsters. No, data analysis. One of the key features, lingos that happens in your department, in your division, is accuracy, recall, precision. Right? Where I am at the 75 Binney Street, Cambridge, Mass, IBM offices. When you go to the data science floor, people are talking about methodologies. They're talking about the confusion matrix, accuracy, recall, precision. I need accuracy, recall, precision because from the confusion matrix is how I get to calculate that true positive, false positive, true negative, false negative. Want to leave you with that this far, and we'll elaborate on it on the next section. Awesome. See you guys soon. Bye bye for now.